Before I begin, Ray asked me to clarify a little bit about the location of the indices. Here, this is how I wrote it, you know. But notice that in reality, you know, what I can do here is I can introduce the unit matrix. I can insert it in between. And how do I write a unit matrix? The unit matrix can be written as the metric times its inverse, you know. So imagine I have a metric here with lower indices, and I have a metric here with upper indices. Nothing changes because this is really like the unit matrix. Okay. So then what I can do is I can regroup indices in this way. Okay, I have this the lower piece of the metric with the lower components. I regroup them like this, and then I have this. You know, I haven't done anything because in reality this combination is the unit matrix. So what you can do is I have the metric with lower indices. What they are going to do is they are going to lower the index. I have an upstairs index. When I contract with the metric with lower indices, I'm going to lower it. So in reality, this is like having an ABC here. And over here, I have a metric with upper indexes. So what it's going to do is going to raise this index. You know. So in reality, I can write this object. I can rewrite it in this form. You know, because what I have done is I have lowered this index and I have raised this index and nothing has happened. You know, so people who work in relativity, what they like when they use the Einstein summation convention, when they contract indices, you know, what they usually do is you contract a lower index with an upper index. You know, this is the notation people use. So this is essentially what I have done here. Now, what happens is when you have a Euclidean metric, there's really no difference between upper and lower indices. You know. There's no difference between covariant and contravariant indices. But in reality, you could write this in this form, okay? You know, so the commutator of these generators can be written like this in this form. Okay, it's the same thing. Or I can raise and lower my indices, you know, you could write it in this form. I mean, it's just a notation, you know. I just wanted to clarify this because Raymond asked me to clarify. It's just a matter of notation, you know. Okay, so let me continue with the rest of lecture number 1, and then we'll do a portion of lecture number 2. Okay, so let me just remind you what this is where we stopped yesterday. We were talking about the structure constants of a Lie algebra. So here, if you work with Hermitian generators, like I said, you could work with Hermitian generators or with anti-Hermitian generators. It's your choice, you know. So you have generators where A ranges between 1, 2, 3 over the dimension of your Lie algebra. And the structure constants associated to that algebra, it tells me the behavior of the commutator or the Lie bracket. So if I have 2 generators, the commutator of 2 generators is going to give me a linear combination of the of the whole generators. So here I use the Einstein summation convention, where I sum over repeated indices. So C will have to sum over 1, 2, 3, 4 over the dimension of the Lie algebra. Of course, in many instances, many of the structure constants are going to be 0. So this commutator may simplify, you know, like when you look at the rotation group, you know, when you take the commutator of 2 rotations, it's going to give another rotation, you know. In general, of course, the structure constants could be more complicated. But the bottom line is when you take the commutator of two generators in general, you're going to have a superposition of the other generators. Okay? And the constants involved in that superposition are given by the structure constants. Okay? I use the letter F. In the book, he uses capital C for the structure constant. C for constant. It's just a convention. Physicists tend to use the F for structure constants, but in your book, he uses the letter C. Okay? Yeah. So the structure constants determine the Lie brackets of elements of a Lie algebra, and consequently determine the group structure of the Lie group. Okay, so there is a representation. Okay, one of the most important researchers in group theory is the theory of representations. I will be not speaking about group representations because it's a highly mathematical topic. And in fact, I noticed that here in your library you have a book devoted to group representations. It's this yellow book by Fulton and Harris. This book over here, yeah. This book over here is in the you have it here. It deals with representation theory, with how to represent groups, which is a very important mathematical area. And actually, most of the research in mathematics of group theory involves in representation theory. But okay, there is a very special representation in group theory which is called the adjoint representation, or some people use the word regular representation. Remember, when you want to work with particle physics, when you work with the Standard Model, for example, you will see that the gauge fields are usually written in the adjoint representation. And the matter fields are usually written in the fundamental representation. But the adjoint representation, basically what it does, remember what I did yesterday? Imagine you have the structure constants. Imagine that you regroup them in this manner, where you extract the first element, the first index of your structure constant, and you assign a matrix to it. And then the last two indices are like the rows and columns of a matrix. So in reality, because the index A ranges between 1, 2, 3, 4 over the dimension of the Lie algebra, you're going to have a collection of matrices, and those matrices is what you belong to the adjoint representations. And when you want to impose the commutator of two matrices, when you look at the commutation relations of your matrices, it turns out that due to the Jacobi identities, you can prove that the commutation relation of these two matrices, remember, this is a matrix that I call matrix number A, matrix number B, and these are the entries of your matrix, the row and the columns. So when you commute these two matrices, you're going to have a linear combination, a linear superposition of the other matrices, and these are your structure constants over here. Remember, when you contract with the index E here, and you contract with the index E here, you are only left with D and C, which are the entries, the matrix entries of the commutator of your two matrices. And the structure constants are your constants that give you the coefficients of your linear superposition. Okay? So essentially, the adjoint representation is that representation that is built from your structure constants. So the structure constants of your algebra allow you to build a matrix whose matrix entries are given by the structure constants. Okay,
you mentioned something about the sparsity of F yesterday, was that right?
The sparsity? Oh, I'm sorry. Pardon.
A lot were zero, yes.
Pardon?
You said that a lot of the coefficients were null.
No. What I say is that, okay, remember, the structure, remember, because a Lie algebra is a linear vector space, you can choose many different bases, right? So usually you want to choose a basis that simplifies the values of the structure constant. So in reality, remember, these structure constants that I wrote down depend on which basis you choose. So if you are clever enough, you can choose a basis that will simplify the algebra, the calculations enormously. And you want to choose a basis that will give the values of the structure constant. You want to choose the majority of them to be 0, and you should select a few which are not 0. But in reality, don't worry about that. It's just a computational, how you say, choice, you know. I mean, it's an exercise in many books in group theory. They say, okay, I give you an algebra, and then they ask you what is the suitable basis you should choose that will simplify your calculations, you know. For example, if I give you a problem, you know, in mathematical physics that has a spherical symmetry, the natural coordinates to use will be spherical coordinates to simplify the problem. Because if you want to use rectangular coordinates in a central force problem, for example, in a spherical problem would be not very wise to use. So you choose your coordinates, you choose your basis according to the problem you want to study. But don't worry about it. In general, the structure constants are the structure constants associated to an algebra. If you change your basis, the values of the structure constants are going to change.
Why is it called a constant?
Because these are numbers. They don't depend on x. They don't depend on the
generators.
the generators are matrices. Remember, this is very important. And the matrices are made out of numbers. You know, they don't vary. They are not space-time dependent. They are constant because they are not space-time dependent.
You mean the F or the T's?
The F's. Yes. The T's are the...
When you say X, you mean X as a space or the generator?
No, space-time.
Space-time X.
Yes. The T's are generators. Remember when I wrote the generators? They are matrices with real numbers or complex numbers.
Yes.
Now the group element is another story. Remember that in order to obtain the group, you have to take the exponential of your generator, and the group elements will depend on your theta parameters. Of course, your group elements have to depend on your theta parameters. They are no longer constant, you know, but your generators are constant, and your structure constants are constant.
So the F is independent of the theta. That's
Yes.
what the
Oh, yes. That's why it's constant. Yeah. Yes. Now, when you work with a group of diffeomorphisms, that's another story, because the group of diffeomorphisms of space-time is infinite dimensional, and in that case, the structure constant may depend on the position. So, strictly speaking, it will not be. It's what you call a soft group manifold. So they are not constant per se. So one has to be very careful. But in this case, the F's are constant. Okay? Yeah, that is more awake today. I'm glad, you know. Okay. Yeah. Okay, so let me give you some examples of groups in physics. Yeah. Since you brought this up of the constant, there's something in mathematics called Lie groupoids and Lie algebroids. It's a branch of mathematics. In that case, the structure constants are not constant. It's what you call groupoids and algebroids, and also when you work with quantum groups.
So what's going on between this constant, non-constant, groupoids, group
The mathematicians now, they want to generalize the notion of a group to something which they call quantum groups. Essentially, a quantum group, imagine when the entries of a matrix. We know that matrices do not commute. Imagine now if the entries in each matrix were elements of non-commuted elements. So quantum groups were discovered by the Russians. It was Manin, and who else? Drinfeld, Manin. They were discovered in the early 80s due to problems of inverse scattering problems. Yeah, and this is how quantum groups were discovered. Quantum groups are very important in quantum gravity because...
Solitons, right?
Yes, integrable models. They're very important because when you're working with quantum gravity, sometimes you have what they call Hopf algebras. Maybe later I can talk to you in person. In other words, when you want to deform the Lie algebraic structure, then you end up with this. Deformations of Lie algebras is what in very pedestrian parlance is what they call Hopf algebras, quantum groups. It's a deformation of your Lie algebra. And people who work in quantum gravity also work with these mathematical structures. It's what you call kappa deformations of the Poincare group. We can talk about that, in a private discussion. But for example, let's talk about the rotation group that you're all very familiar with. Is the symmetry group of Euclidean three-dimensional space. Well, and all fundamental laws of, this is in classical physics. In Newtonian mechanics, the rotation group was very important. You know that. When we study mechanics, for example, when you have a rigid body and you look at rotations of a rigid body, we know how important the SO3 group was. Remember that when we study classical mechanics, we have to look at the Euler angles. Remember when we study Hamiltonian mechanics? Now the Lorentz group, remember the Lorentz group is an extension of the rotation group where now you add one temporal dimension. This 3 means your 3 special dimensions of space-time, and 1 is the time. Okay, so space-time in 4 dimensions, you have a very important group, which is the Lorentz group. Remember, you can work with the higher dimensional version of the Lorentz group. The only thing you do is add more spatial dimension. You keep 1 temporal dimension, and you add more than 3 dimensions. You can have 4 spatial dimensions, 5 spatial dimensions, 26 spatial dimensions, as many as you wish. The only thing you do is you keep the 1 because you have 1 time, and you add more spatial dimensions. But the group structure is basically the same.
Some study with 2 times also?
Yes, but in that case you will have a 2 here and a 2 here. SO2, 2. Yeah, it all depends on the signature of your space of your metric, So the Lorentz group we know is a symmetry group of 4-dimensional Minkowski space-time with special relativity. When we have a flat space-time, we know how important the Lorentz group is. And when you look at the commutators of the Lorentz algebra, look, I wrote the algebra in lowercase letter here to differentiate from the group. This is the group. You use capital letters. For the algebra, you use lowercase letter. And when you look at the commutation relation, it's more complicated. Now you're going to say, why do I use 2 indices instead of 1 to label the elements of my algebra generators? I use 2 indices here because now we're going to have rotations along the 1-2 planes, which is the XY axis. I have a rotations along the 1-3 plane, which is a rotation along the X Z axis. And they have rotations along the 2-3 plane, which is the Y Z axis. So this is a way of naming. Okay, you want to have rotation about you're going to have 3 planes. We have the 1-2 plane is the floor that I'm standing on. The 1-3 plane could be this wall over here, right? And the 2-3 plane could be that wall over there, okay? So you have 3 walls. So I could have rotations around this plane, rotations on that plane, and rotations on the window, okay? Now, in relativity, you're going to have also what they call Lorentz boost generators. Remember that when you have an observer moving at a uniform velocity with respect to another observer, suppose I was moving with a certain velocity relative to all of you, then you have to, in relativity, you need to tell us how the coordinates and how space-time transform from one frame of reference to the another. So a boost transformation is just a transformation. Okay, now you see I have a 0 here, a 0 here, a 0 here. This 0 represents like a rotation in time. Rotation, quote unquote, because a Lorentz boost in reality. A Lorentz boost is nothing but a rotation with an imaginary angle. Imagine you have an angle which is purely imaginary, and I perform a rotation with an imaginary angle. You get a boost. So When you have a boost along the x-axis, it's like a rotation in the time x-axis. When you have a boost along the y-axis, it's like having a rotation along the time y-axis. And then boost along the z-axis, it's having like a rotation. I mean,
so the time also has x, y, z?
no, the time is time. But because you have 4 dimensions instead of 3, you have 6 planes. You have the 6th plane is you have one plane which is the floor, one plane which is the screen, another plane which is the window. Then when you add the extra dimension, you have to include the xt combination, the yt combination, and the zt combination. Okay, so this is what m represents here. Okay.
Basically, that 0 dimension is...
The 0 is the time. The time. Okay. Yeah, I use the time because physicists like to use notation 0, 1, 2, 3. Other authors use 1, 2, 3, 4. It's just a convention.
So you can choose acceleration, which is some notion of time,
Yeah.
of any of these planes or the combination of them.
Yeah.
That's the reason why
Yeah.
this makes sense.
Yeah. Yeah. So now when you look at the commutation relation, because now the generators of the Lorentz group, now I choose to index, to label the generators using 2 indices, okay? Because to remind me what is the physical interpretation of each generator, okay? So now when you look at the algebra, the algebra is given by this, the commutation of 2 generators. Remember, my indices mu, nu, rho, and sigma range between 0, 1, 2, 3, and 4.
Is
Okay.
that typo? Should that be M or L? The last one?
The last one?
Top, the equation?
Ah, yes, it's a typo. I'm sorry. L means Lorentz. Lorentz. And M, yeah, it should be, yeah. It should, an M, yeah. So when you take the commutation relation between 2 generators, it's going to be given by a linear superposition of the other generators, you know. Now here, what do you have here? Here, notice I have a mu here, and then here I combine it with a sigma, and I get G mu sigma is the metric. It's a metric. Is the space-time metric here. So the space-time metric appears here, 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 and here. So of course, this is the mu sigma component of the metric. You know, remember the metric is in 4 dimensions. The metric of space-time is a 4 by 4 matrix. It has 4 rows and 4 columns. You know, so here mu sigma means the entry, the mu sigma entry of my matrix. Okay, and here is my mu rho entry of my matrix. This is my new row and entries of my matrix, and this is the okay. So let me give you an example.
G plays the role of the structure constant.
Yes, in a way, G will. Yeah. So remember, here I'm using the space-time metric. So if I'm working with Minkowski space-time, the G mu nu is a diagonal metric, and it depends on which signature you want to use. If you want to use a minus, plus, plus, plus signature, then it depends on the signature you want to use. Okay, so usually the Minkowski metric, people write it like this, you know. So you can use, it could be minus if you assign the temporal direction minus. You said, okay, this is a diagonal matrix. You can use this signature convention, or you can use this signature. Okay, so this means, you know, that you have a matrix. Okay, you have a 4 by 4 matrix. So if you use the first convention, if you use this signature, that means that the 0, 0 component of the metric is -1. Okay, and the other components of the matrix are 1, 1, 1, diagonal. Okay, this is the x component of the metric, this is the y component, and this is the z component. And this is the temporal component of the metric, which is, you can write G time, you know, this is what I label G sub 0 sub 0. So in that case, for this choice, it's equal to -1. Now, if you use the other signature, you know, it's just a convention. Then in that case, the temporal component of the metric, in that case, will be a plus if you use this signature. And the others will be minus, minus, minus. It's just a convention, you know. So, okay, so I'm going to give you a explicit example. Yeah. So let's suppose I have a boost along the z-axis. Let's suppose I have an observer that is moving upwards towards the sky.
Does a boost mean acceleration or constant?
No, acceleration means it's a person who's moving with constant velocity relative to a frame of reference that is at rest. So imagine I have two observers. One observer are, for example, you, us, and then imagine you have another observer that is moving at a constant velocity b towards the sky or towards the earth, you know. It's moving upward or downward, you know. Imagine this is the generator of boosts along the direct axis number 3, okay? Along the z-axis. Imagine you want to take the commutator with a generator that is given by the rotations about which plane do you want to choose? 1, 2, 1, 3, 2, 3. Which one would you like to choose? You know, just
1, 3.
1, 3. You want to choose 1, 3. Okay, you want 3. Okay, so what you do here is, according to this formula, okay. Yeah. What I have here, this is what I call mu here. Mu is 0 in this case. Nu is 3 in that case. And then rho is 1. And sigma is 3. Okay? So this is the, I'm sorry, sigma is 3. Okay? Okay, so the first term is given by G mu sigma, okay? And what did I call mu? Mu I call 0, right? This is 0 here. Sigma is what I call 3. Okay, you put the 3 here. Okay, and then I have m. And then I have nu rho. And what I call nu is what I call 3. And rho is what I call 1. Okay? Yeah, and then you fill in the entries like that. Minus, okay? And then I have mu rho, okay? What I call mu is 0. What I call rho is 1, okay? M over there is nu sigma. Okay, so what I call nu is 3. What I call sigma is 3. And then, you see what I do, okay? You just, is that okay, Fang? Or you want me to spell all that? I can spell all the terms if you,
That's fine.
that's fine. Okay, yeah.
I didn't follow the top line. I probably missed something you said. The
Top?
G, yeah, the definition of the first, is that m mu equal to the 2, the plus minus minus?
Yeah, this is the Greek letter eta. Oh, is it eta or theta? Eta. Okay, let's call it.
Oh,
Okay.
So it's the same as the G here.
Yes.
But then you have the G mu equal to the 2. The 2 are like,
No. Yeah, go ahead.
yeah, so it's the top is minus plus plus plus. You said it's either that or you can do the plus minus minus minus.
Yes.
And so then the G00 equal to minus 1 half.
Ah, that was before. Okay, let's do like this. Minus, plus, plus, plus.
Okay,
Or let's have it like this. Plus, minus, minus, minus. Okay? Okay.
So I was
No.
Not what is this formula.
Well, I mean,
Minus G00.
well, I mean, okay. In that case, I mean, it depends. This could be minus or plus. Depends on.
GTT is not G00.
No, it's what I call TTT for me is 0. T is time.
T, oh,
T is time.
T, yes.
Okay, d'accord? Yeah.
Carl, Carlos,
Yeah.
you said that the generators are constant matrices, right? We saw that earlier. They are numbers.
The numbers, yes.
Correct? They are
Well,
numbers.
they are numbers when you present them as matrices. Yes, yes, yes. Yeah.
So it makes sense that the boost M03 is constant. So we're not talking about acceleration; it's a constant velocity.
But yes, of course. Remember, the Lorentz transformations involve velocity, constant velocity. When you work with acceleration, then you have another group. When you have acceleration boost, you have another group.
What is it?
You could call, people call it the coaplectic group. Coaplectic group. Yes,
So
yes.
this doesn't take into account acceleration?
No, no, no. You could have acceleration. No, acceleration, the velocity has to change. You could have acceleration if you have a continuum of observers, and each observer has a different velocity.
So you cannot have a concept or a notion of generators which are functions of time. Can you?
Well, in that case, no, because, well, in that case, the boost parameter is a constant. If the boost parameter is a function of time, then you have another entirely group structure. You have the coaplectic group, you know. You could have constant accelerations. You and I right now are experiencing a constant acceleration,
The relative acceleration.
which is the force of gravity. The gravity, the floor is exerting a force on our feet. So you and I, and he, we are not in an inertial frame of reference. We are not in free fall. So in reality, all of us are in accelerated frame of reference. Yeah, that's true. At this very moment.
But in relation
Because there
to
is
each other.
gravity.
Because of
We're in a gravity.
yes.
But in
Yeah.
relation to each other, we are not accelerating. That's why
No.
it's not a function of time.
No, no, no. Okay, so, okay, now, when you look at the components, this is G sub 03. It's, remember, when I have a diagonal, it's 0 because the diagonal matrix, this is 0. Then this is also 0. And then, okay, but then I have to have the third term. Let me just write the third term. What is the third term? G.
Another zero.
Nu- you also have another 0 there? Okay, and then the only non-zero must be
The last one.
the,
G new sigma.
which mu sigma 3, and then the other combination must be mu rho 0, 1. Okay, so basically, okay, so which signature do you want to use here? Plus or minus 1? For the metric, which one do you want to use? Which choice of G33 you want? You want a plus 1 or a negative 1? You want a plus? Okay, so you get, for this choice, you get this. Okay, so physically, what does this mean? This means that, that when you have a boost along the third axis, so the commutator of a boost along the third axis, with a rotation along the 1-3 plane is going to give you minus a boost along the x-axis. Okay, that's physically what it means, right?
Is rotated.
Yeah, the boost is rotated, yeah, okay.
And if it was M12 with no common index, then it's it's 0. 0, 3 and M1.
Ah, yeah. I mean, remember, in order for this not to be 0, you have to have at least some common index.
Yeah.
Because if there is no common index, then that means that the entries of the matrix component will be off diagonal, and we know that the entries of the organ off diagonal will be 0. You're right. You have to have some common element between the generators. Otherwise, of course, you'll get 0.
Seems like you have 0, 3 and 1, 3,
Yeah.
and then you just cancel the 3 and you have 0, 1.
Yeah.
Go to the 3 to 1.
Yeah. No. Did I misrepresent the notation here?
No. I'm just like thinking it in
Yeah.
because you have a 0, 3 at the beginning, and then because there's a rotation of from 3 to 1, or
Yeah.
from 1 to 3,
Yeah.
and then so basically that original 3 becomes 1.
Well, in other words, it's like the 3 cancel somehow, and you end up with 0, 1. Yeah. Yeah. Okay. And okay, like I said, that the above commutation relations are valid for the Lorentz group in a d-dimensional space-time. When you have a d-dimensional space-time, you have d minus 1 spatial dimensions, and you have 1 temporal. So when you add the spatial dimension with the temporal dimension, you have capital D. Okay? Yeah. Can I proceed? Okay. Now, the Poincaré group. The Poincaré group is also a very important group in physics, because now you're going to combine Lorentz, you're going to have rotations, you're going to have Lorentz boosts, which is, when you have an observer that moves with a constant velocity with respect to another observer. And then you have something else which is called translations. The translation group is, which should not be confused with Lorentz boost. The translation is simply when you displace the axis of coordinates, let's suppose that the origin of coordinates is given by this point here in the corner. Now, if I want to displace my axis by a rigid translation, I can displace my axis where I'm standing right now. So I have performed a translation along this direction here, and then I'm sitting here. So the P's are the translation generators, In mechanics, remember, P1, P2, P3 are like the momentum the generators, and P0 is like the energy. Remember the energy momentum operator in special relativity? P0 is like the energy, and P1, P2, P3 are like the spatial components of the momentum. Okay, so the Poincaré group is given by, you see this product here, this direct product, you see this letter S? This letter S means semi-direct product. And why is it called semi-direct product? Because notice that the translation generators commute with each other. You have really an abelian group. But the translation generators do not commute with the Lorentz generators. You see, when you perform the commutation of a translation with a Lorentz, you get a linear superposition of translations. Because they do not commute, the translations do not commute with the Lorentz group, this is why you use the letter S here, semi-direct. Okay? Let's suppose that the translations commute with the Lorentz group. In that case, you will remove the letter S and you'll have the direct product. So in this case, the Poincaré group is the semi-direct product of the Lorentz group with the translations, and this is how it's written. The translations, I'll write here R sub D, is like having the translations, in Euclidean space. Well, not really Euclidean, it's really Minkowski space. In order to be rigorous, instead of D here, I should have written D minus 1, because I have D minus 1 spatial directions, comma, D minus 1, comma 1, in order to be rigorous, But I was a little bit sloppy here, and I just wrote D for D dimensions, okay? So the Lorentz group is given by, the commutators of translations is 0. The commutators of a Lorentz with a translation is given by this. And then, of course, the commutations of the Lorentz is given by this, okay? So the Lorentz group is one of the very, very important group in physics, because you're dealing with the symmetry group in flat space-time. Is the relativity? It's the special relativity group. When you want to construct a quantum field theory in flat space-time, the Poincaré group is essential.
Just to clarify.
Yeah.
The capital D on the real space R.
Yeah, R is.
Referring to the Euclidean.
Yeah, in reality,
Not time dimension.
it's not Euclidean. I should have written it like this: capital R, pseudo-Euclidean space. If you want to be rigorous, RD is Euclidean space. RD minus 1, 1 is pseudo-Euclidean. Let's say Riemannian, a flat Riemannian space, R. Okay? I was a little bit sloppy, but the rigor is you should say that You should specify the temporal dimension. You should separate it from the spatial dimension, you know? Okay? Okay, because otherwise you will end up with rotations in 4 dimensions instead of rotations plus boosts. Okay? Yeah.
So,
It's
you
yeah.
have translations on the right side.
Yeah.
You can translate time.
Yes, of course, of course. Yeah. An example is the Hamiltonian. The Hamiltonian generator is the generator of temporal translation. Remember in mechanics, in non-relativistic mechanics, in Hamiltonian mechanics, the Hamiltonian is the generator of temporal translation.
Can you explain what is boost and the time interval? I said, can you explain?
So, yeah.
I heard her call you please.
Fang, I'm sorry. Yeah.
I'm asking if you can explain the boost again, the boost in the time axis.
Yeah. Well, when you study relativity, remember the Lorentz transformation that I'm going to write down in a minute. The Lorentz transformation. Remember when we look at how do the x and time coordinate transform from one frame to the other? Let me write them down. Remember when you have how do 2 observers measure the length of the rulers and the readings of their clocks?
Oh, that's the boost. Oh, okay.
That's what it was.
Yeah, yeah.
Okay.
Yes.
Is it analogous to the when you're
Yeah. Well, actually, in a few minutes,
space time?
in a few minutes, I'm going to talk precisely about boosts. I'm going to write down everything. In lecture number 2, at the beginning of lecture number 2, I'm going to write everything about the Lorentz group. You know, if you know, in a few minutes I'll write about that. Yeah. Now the special unitary group is the symmetry group in quantum chromodynamics. Remember when you have quarks and the 8 gluons, you have 3 quarks and gluon. SU3 was the 8-fold symmetry. It's this is the group that governs a strong interaction. The symplectic group, remember that when we work with the symplectic group, we have to work with an even dimensional space because it's the group associated with Hamiltonian mechanics. When you work with Hamiltonian mechanics, you have to work with coordinates and momenta, coordinates and momentum. So this is the symplectic group, is very important. Then the SO32 and the E8 cross E8, remember during the string revolution in 1984, these groups appear in the 10-dimensional superstring. Okay, let me explain. By the word super, when people use super in superstrings, the word super means supersymmetry. That's where the word comes from. It doesn't mean Superman, super wonderful world.
Symmetry, gravity.
It means supersymmetric strings. When you impose supersymmetry in string theory, you attach the word super. So what happens is that people in 1984 actually, John Schwartz and Brian Greene, they were actually at Caltech and in England, Queen Mary College in England. Michael Greene in England, and John Schwartz at Caltech. They were very happy because they discovered that you see, when you do quantum field theory, you have to be very careful that when you impose quantum mechanics, when you implement quantum mechanics into field theory, you have to be very careful that you don't have anomalies. See, anomalies is something that destroys the symmetry of the theory. Okay, when you do quantum field theory. Anyway, the bottom line is that the SO32 and the E8 cross E8 are the groups that were free of quantum anomalies. And this is why people were very excited in 1984 that you might have a theory of the world, you know, the theory of everything. Remember, back in 1984, well, I guess you were very, very young. So SO30, you see SO32, look, E8 and E8, the rank of E8 is 8. The rank of E8, so 8 plus 8 is 16. So SO32 is a rank 16 group. So the Cartan-Sov algebra is that you have 16 generators. So these groups were very popular, you know.
But in fact, yes, this time,
Yeah.
not any of my physics teacher was able to explain what this was. So it was not so exciting
Yeah.
because they were not able to explain. They were just drawing string, open string and closed string,
Yeah.
and that's all.
No, but remember, when you look at the books, there's something called quantum anomalies. So if the theory has anomalies, then the theory is sick. It has to be free of quantum anomalies. So these groups were the only ones that were free of quantum anomalies. So this is why people were very excited, okay? Now, at the end, next week on Friday, at the end of my 10th lecture, I will talk a little bit about the E11, okay? Remember, E11 is an extension of E8. In 1968, you had the Russian mathematician Victor Kac and Robert Moody invented what they call Kac-Moody algebras. Kac-Moody algebras are an extension of the classical algebras that we know about, okay? And I will talk a little bit about how they came up with this concept of how to extend the classification of Lie algebras to include what they call an infinite number of generators, okay? Which is what they call Kac-Moody algebra after the mathematicians Victor Kac and Robert Moody.
What's
So,
the USP or what's the reason for infinite number of generators?
Infinite number, because in string theory, you actually have a conformal symmetry in 2 dimensions, and the conformal group in 2 dimensions is infinite dimensional. Because you have these holomorphic transformations, like conformal maps, and you could have an infinite number of conformal maps that preserve the angle. So it's what you call the Virasoro algebra, and it's infinite dimensional. Later next week, I'll also talk about Lie algebras and quasicrystals. So you're going to have, I'm going to talk about a Lie algebra on a Fibonacci chain, and you're going to have an infinite number of generators in a Fibonacci chain. So that algebra is infinite dimensional also.
Does it always that the quasicrystal has to have infinite?
This kind of algebras I'll be talking about, yes. Yes. So E11 is an extension of E8, okay? And E11, according to Peter West in England, he claims it's a symmetry of 11-dimensional supergravity. But supergravity means includes gravity and also the word supersymmetry, where instead of having the graviton, you also have a particle, a spin 3/2, which is called the gravitino. The gravitino is the super partner of the graviton. The graviton has spin 2, the gravitino has spin 3/2, and this is what they call supergravity. So 11-dimensional supergravity has this symmetry E11, which according to Peter West is the symmetry of the world. This is what he claims, you know. But remember M theory. Remember that Witten is the one who coined the word M theory. Yeah.
Supergravity in superstrings there is no gravity.
Yeah, of course. No, in supergravity is the low energy limit of superstring theory. Yeah, it's the lower because remember in strings you deal with extended objects. In supergravity you deal with point particles. In strings you deal with extended objects. Remember in string theory, when you look at the vibrations of in string theory is like when you have a guitar. When you plug a guitar, the modes of vibration, you know, gives you a note, and each note gives birth to a particle. So in string theory, particles are viewed as the notes of a guitar string. When you play, the different notes of vibration give birth to different particles, to different states of excitation. So supergravity, you deal with point particles. In strings, you deal with extended excitations of the string or a drum and so forth. Okay? Yeah. Now, M theory is a word that Witten coined. He coined this because M stands for mystery, mother, matrix. You know, well, since you are here, after all, this is something very important. The second string revolution that happened in the early 90s or mid 90s has to do with string dualities. The notion of dualities is that you have, imagine you have a cube with 6 faces. You know, in reality, you have one cube that manifests itself in 6 different ways. So this is what you call dualities in string theory. They are different faces of the same cube, okay? So in string theory, let me see if I remember because it's a while back, you have what you call type 1 strings, which are really open strings. You have type 2 strings, which are deal with strings which are closed. And then you have 2 types of strings. You have type A and type B that have to do with the chirality of the modes of propagation. You could have left-handed, right-handed. So close, you could have modes that move clockwise or counterclockwise. You know, when you're in a circle, you can move clockwise or counterclockwise.
There is also something with fermion and boson.
Well, when you have supersymmetry, you have bosons and fermions, both.
But not in the one.
No,
Boson or fermion.
no, you could have both. You could have bosons and fermions on both. What happens is that the type 2 strings have gravitons. You know, gravitons appear in type 2 strings. And in type 1, you don't have gravitons. Okay, gravity appear in closed strings, type 2. Okay, then you have the SO32. You know, heterotic string. You see, the word heterotic means in Greek, heterotic means hybrid. It's just a word. They wanted to be fancy. Those guys at Princeton, you know, they like to come up with fancy word. So the word heterotic means hybrid. And this is the E8 heterotic string. Okay, these are the heterotic string. Okay, and then you have 11-dimensional supergravity over here. 11-dimensional supergravity that people like to condense the notation by writing it like this: supergravity. Okay, and remember, these string theories live in 10 dimensions, but supergravity lives in 11 dimensions. You know, so what happened is that this mystery theory, these were corners. These theories were faces, different corners of, of the cube. You know, imagine you have different corners of a theory. The theory has different manifestations, you know, different forms, and they're all related to each other. There's what they call dualities that map one theory into the other. So Witten gave the name to this unknown theory, this mystery theory. He gave the name M, which stands for mystery, mother, and then later on they use the word matrix, you know. So that's the word they use, okay? Now later on, Baffa, who was a student of Witten at Princeton, that I met him many years ago at MIT, he's from Iran. Later he claimed that the fundamental theory was not 11-dimensional, but it was 12-dimensional. And there's a theory in 12 dimensions, which has to do with a signature of 10,2. Yeah, 2 time-like directions. Is what he called F theory. And the F word, because he wanted F for father. You know, father, M for mother. Anyway. Now, the E11, which is an extension of the E8, apparently is a symmetry that is somehow in here. Okay? So since you are working with E8, I think it's in the future, think about this affine Kac-Moody extension.
It's linked to the Jordan algebra.
Yes, yes, yes. So anyway, since you're working with E8, don't worry. You'll become acquainted with this very soon. Okay? Okay. Yeah.
How is
Yeah. Yeah.
the graviton, does that indicate the graviton
Yeah.
has a chirality?
Well, the graviton has polarization, you know, because it has spin 2. So the helicity is plus minus 2. A graviton is massless, and the helicity is plus 2 minus 2. You know, well, remember, chirality mainly deals, with spinors. Okay, chirality has to do with left-handed, right-handed spinors. The graviton has spin 2. It's a boson. It's not a fermion. The gravitino has spin 3/2, and the gravitino is a fermion. So with the gravitino, you can speak of chirality, yes. With the graviton is boson, you don't speak about, it's not a fermion. So you don't speak of chirality with a photon because the photon is a boson, it's not a fermion. However, there is something you can speak of called the helicity, plus minus 2.
So
Okay.
it's not single-handed, right?
No, it's a boson.
You
the,
put in the type 2A, type 2B, as well you said type
well, no, what happens is that the graviton, because you're dealing with, when you have supersymmetry, okay, so let me just write it down. Then you're going to have, this has spin 2, okay, and then the gravitino, you write it like this, gravitino, you write, and then you have a bosonic index and the fermionic, it has spin 3/2, okay? And the chirality had to do with the fermions. You know, the fermions that move clockwise or counterclockwise, the fermions that move clockwise can have the same chirality or opposite chirality with respect to the fermions that move counterclockwise. Okay? So you have clockwise moving fermions, counterclockwise moving fermions, and the fermions that move clockwise may have the same chirality or opposite chirality with respect to the fermions that move counterclockwise. So, okay?
The difference between A and B are the counterclockwise or clockwise.
It has to do with the difference in the chirality of the clockwise fermions versus the counterclockwise fermions.
So the graviton then can be in type B or type
Yeah, but it can be on both.
Okay.
Can be on both. Yeah,
So
yeah.
it's going to be.
Yeah. I have to review my string theory because it's not that, you know, yeah. Okay, now let's go to the conformal group. The conformal group is probably one of the most important groups in physics. Okay, so like Amir said, the conformal group is the group of transformation from a space to itself that preserves all angles within the space. The group of conformal transformations of the n-dimensional sphere is generated by inversions in circles. The group is also called the Mobius group. Okay, I wouldn't worry too much about the Mobius group, but think of the Mobius group appears when you look at the conformal transformations of the sphere or the higher dimensional versions of the sphere. Don't worry too much about the Mobius group for the time being. The conformal group is this. The conformal group in D dimension is like rotations in a D plus 2 dimensions, where you have 2 temporal directions and D spatial dimensions. So think of the conformal group as generalized rotations in D plus 2 dimensions. That's all you have to think about. Where 2 are like 2 temporal dimensions and the spatial dimension. That's all you have to think about it. Now, in the conformal group, you are going to have the ordinary Lorentz generators, the translations, the dilations, which would generate scalings, dilatations, scalings or contractions. And you have something which is called the conformal boosts. The conformal boost, in fact, you can think of the conformal boost as something which is related to accelerations. Okay, so in a way, the conformal boosts, you can think of them as quote unquote accelerations. Here you have the Lorentz boost, as I showed earlier, but the conformal boost. Okay, conformal boosts consist of three things. A conformal boost, you have to perform an inversion. By inversion, imagine you have x goes to 1 over x. It's like an inversion. Followed by a translation, and followed by a second inversion. So the conformal boost consists of three operations. You have to invert, like imagine you have a radius vector, and you invert it, is r goes to 1 over r, followed by a translation, followed by an inversion, the conformal boost. I will give you the reference. I mean, it's just, imagine you have a vector as a vector, So imagine what I want to do is I want to find an inversion, okay? So an inversion, imagine I multiply and divide by the same thing in a very pedestrian way. Let's suppose I multiply upstairs by r, and what I do here, I take the scalar product of r with r. So I have a modulus square, and here I have r over here. So this is what you call an inversion. And essentially it's like taking a vector and going to 1 over r. It's like taking the number 3 and you invert the number 3 as well. Well, it's an inversion. Okay, this is the first operation. You invert. Then you have to translate. Okay, so then you have to perform a translation. Let me write here. Okay, you perform an inversion. Then you translate. Okay, you add another constant, a constant translation, and then you invert again. Okay. And then you invert again. So essentially, this is what you call the conformal boost generators, okay? It's just a 3-step process, okay? It happens that the conformal boost is related to accelerations, okay?
So, So remember how you told us the generators, they were all constant elements, and you have the boost generator, Lorentz boost generator, which is also a constant.
Yes.
How does all that translate in this language?
Yes. Well, I'm going to write the generators. Okay. Remember, there's something in group theory called a representation, and another thing called a realization. Okay. A realization of an algebra is you want to realize the generators as differential operators, and a representation is when you realize them as matrices. Okay, I'm going to talk about this, the difference between a matrix representation or a realization in terms of differential operators. Okay, I will talk about both things. So let's suppose that you want to look at the conformal group in 4 dimensions. Okay? The conformal group in 4 dimensions has, let's say let me just, red is better, or black or red. Yeah. Okay. Let's suppose I look at S of 4, 2 rotation. Okay. So the total number of generators is what? It's like rotations in 6 dimensions. So I have 6 times 5 divided by 2 is 15. Right? 15 generators in total. So I'm going to have the Lorentz generators are going to be 6 Lorentz generators, which in reality means I have 3 rotations and 3 boosts. Okay, rotations. Okay. Then I have something which I call the conformal boost generator. I'm going to have 4 conformal boost generators. I have 4 translations. And I have the dilatations. I have one generator. So when I add them, I have 1 plus 4 is 5, plus 4 is 9, plus 6 is 15. I have a total of 15 generators. Okay? So I have 1 dilatation, 4 translations, 4 conformal boosts, and 6 Lorentz generators. Okay? Yeah. Yeah. He talks about the conformal. Yeah. But it does talk about the conformal group. Yeah. But anyway, also in the lectures, I usually give you references. At the beginning of each lecture, I give you the table of contents, and also I give you the references where you can look these things up.
Okay, so what is the reference?
Here, let me just go to the conformal group. You can look at also. Okay, what is the number one source of reference? Wikipedia, right? Wikipedia, and even better, Scholarpedia. You know there is a Scholarpedia too. The Scholarpedia are peer-reviewed. It's like Wikipedia, but it's peer-reviewed. Tu connais Scholarpedia? Write it down. It's a Scholarpedia, yeah. Yeah. How is it going? Is it fine? Yeah.
How do you spell that?
A scholar and you add pedia.
Google
Yeah.
will correct your spelling anyways.
Yeah. A Scholarpedia, yeah. The conformal.
This guy just gives a table, there's not much more.
No, he talks about the conformal group in there, yeah. Yeah, no, this book is an old book, but it's very good. It also has many exercises. Like Raymond said, the only way to learn things is by doing problems. It's the only way you learn. Otherwise, it's impossible to learn without doing the problems, you know. But remember, this is a textbook in many courses. So when you take a semester course of group theory, or sometimes 2 semesters, when you look at represent, they give you a lot of problems and they're not easy. Some of the problems are hard, you know. Okay, so remember, in two dimensions, there's an infinity of conformal maps because they are holomorphic mappings. In 2 dimensions, you can work with the complex numbers. When you have holomorphic functions, when you make any coordinate transformation, the Z variable goes to the C prime variable. There are an infinity number of them. So in 2 dimensions, the conformal group is infinite dimensional. You know, in more than 2 dimensions, the Euclidean conformal transformations map circles to circles, hyperspheres to hyperspheres, and straight lines to straight lines. In other words, the conformal group maps circles to circles, spheres to spheres, lines to lines, hyperplanes to hyperplanes. This is why, geometrically speaking, the conformal group is very, very important. And then later on, when you study twistor theory, remember twistors were invented by Penrose, and the conformal group was essential in twistor theory, you know. And I'm sure since you'll be working on quantum gravity, you'll encounter twistors in the future, you know.
Carlos,
Yeah.
these are restricted operations, right? Because obviously, if it's a null vector, you're going to get a blow up.
Yeah.
So how do you?
Yeah. I know, when you have a null, yeah. But remember, in conformal transformations maps null lines to null lines. The conformal group preserves the light cone. The light cone is not deformed. The celestial sphere, when you look at the night sky, the celestial sphere and the conformal group remains a sphere, remains a sphere. Remember, the Lorentz group, when you look at the Lorentz, let's suppose that you look at the night sky and you have a star that moves at a constant velocity with respect to you. So if you look at the Lorentz group transformation associated with that star that is moving with respect to you, so you look at the celestial sphere, the Lorentz group transformation look like conformal transformation when they are projected at infinity. When you look at the projected group, so when you look at the conformal sphere, I will see if I can find a very nice article explaining the connection between the Lorentz group and the conformal group. So the conformal group, when you look at the Lorentz group and you look at transformations at infinity, the conformal group looks like the Mobius group. So the bottom line, the conformal group maps spheres to spheres, circle to circles, line to lines, hyperplanes to hyperplanes, you know. Yeah.
Would Mobius transformation to R2
No.
classify as
No, Mobius transformation. Mobius transformation. It's you know, if I remember, the Mobius transformation in the complex plane. In the complex plane, remember, it has to be in the, you know, where yes, a fractional transformation. B C z plus D. In other words, you take a complex number and you map it to this. Where now, of course, you want to impose the condition that AD minus BC equals to 1. Okay? So this is like a Mobius transformation.
Bilinear transformation.
And this transformation, in other words, the Lorentz group is related to this. It has to do with the behavior of the Lorentz transformation at conformal infinity in the celestial sphere. And the Mobius group, people write it, is the special linear group to complex. You know, this is what the Mobius group. Some people call it the fractional linear transformations in 2 dimensions, but in reality, from the Mobius group, this is the Mobius group, okay? But it happens that it's also related to the Lorentz group, okay?
We will study it more. No?
I'm sorry?
We will study SL2C more.
Yeah. Because when you look at the number of generators, this has 4 minus 1, 3, but because it's a complex, 3 times 2 is 6. So the 6 generators is related to the Lorentz group. And it has to do with the transformations of the Lorentz transformation at infinity, at conformal infinity, at the celestial sphere. The Lorentz transformation look like this when you look at infinity. Okay? And this is why Penrose came up with the idea of twistors. Okay? Yeah. Do you have any book on twister theory? On
Yes,
twist?
the road to reality.
The road to okay. Well, Penrose in his book expresses it really well. Yeah, take a look at Penrose. Yeah, the book is about 1,000 pages, remember? And he has very nice pictures. I mean, he's the one who
Written by Penrose.
he invented it. Yes, yes. Take a look at Penrose's book. Yeah, yeah. Look at the word Mobius group, conformal group. Yeah. Now let's look at the commutation relation of the conformal group. Okay. The non-vanishing commutators are given like this. When you take the commutation of a dilation with a boost, it gives you a boost. Again, I'm using Hermitian operators, and because I'm using Hermitian operators, I have I's and I's here and I's here and I here. I here, I here, I here. If I work with anti-Hermitian generators, then you get rid of the I's, okay?
Which letter corresponds to the conformal boost?
The conformal boost K. P is translation, P for Poincaré, K is conformal boost, okay? So the commutation of a dilation with a conformal boost gives you a conformal boost. A dilation with P gives you this. The commutation of a conformal boost with a translation gives you a combination of dilation and Lorentz transformation. And then, of course, when you take the Lorentz group, which is like a rotation with a K, gives you a linear combination of Ks. The commutator of P with a Lorentz generator gives you a linear combination of rotations, of translations. And the commutation of 2 rotations gives you this. Okay? These are the commutation relations, the non-vanishing commutation relation. Because I only write the non-vanishing one. You know, the others give you 0, so that's why I don't write them. Because imagine you have 15 generators. Imagine how many combinations can you have. You know, you can write, you can fill many pages of commutation relation. But since most of them are 0, I don't write them down. Okay? Yeah. By commutation relation, I mean non-vanishing commutation relations. Okay? Yeah. Yeah. Okay, now the conformal group, okay, remember, I talk about a matrix representation, now I'm talking about a realization. You see, there's, again, I want to emphasize, there's a big difference between realization and representation. By representation, people mean a matrix representation of your Lie algebra. By realization, you talk about a realization in terms of differential operators. Because I mentioned yesterday that a continuous Lie group has a smooth structure associated with it, so they are now, remember, okay, so remember, this is like a, okay, let me tell you where this comes from. Yeah. Can I erase this? Yeah. Remember when you studied quantum mechanics, remember what the orbital angular momentum operator was? In ordinary mechanics, the orbital operator is like the cross product of R with the momentum. Remember in your classical mechanics courses that when you take the cross vector of R with P gives you an angular momentum? Yeah. Remember, the orbital angular momentum, okay? This is orbital, okay, equals R cross P, remember? And in quantum mechanics, remember the momentum operator looks like a gradient operator. Remember in quantum mechanics? Yeah, when we studied the Schrodinger equation, 2m plus the potential acting on the wave the wave function. This is like the Hamiltonian, and this is like IH bar partial of phi respect to t. Remember? So the Hamiltonian is like a derivative operator. Remember? And the p. Remember the p? You replace the p by the p operator by minus h bar gradient operator. Remember in quantum mechanics?
H bar k.
Yeah. So okay. So essentially, so this is like having the x operator, which is here, and then cross with a differential operator, because the momentums is like taking the derivatives, right? Well, okay. Let me write the indices, all the indices below. Okay. Now, because the generators are antisymmetric in the indices, remember that the generators are antisymmetric in the indices. Remember? These are antisymmetric. When I reverse the indices, I flip signs. Then I want to antisymmetrize with respect to the indices. So I replace mu by nu and vice versa. Okay? Okay. So this is what I did here. Yeah. You see here I have mu nu and then minus nu mu here, because I need to have antisymmetry with respect to the indices.
There's notation also with the
Yeah.
commutator.
Yeah, so this is what I mean, partial derivative with respect to nu. This is what I mean by this object here. It's just a notation, where people call this, but they like to abbreviate things. They call it, this is the symbol they use. And here they abbreviate by calling this partial with respect to mu. It's just an abbreviation,
Carlos, can I ask a question?
And then I'm going to write the commutation relation using differential operators. Yeah.
So you made a point about realization as being distinct from representation.
Yes.
Right?
Yeah.
So
Here I'm using differential operators because I have a realization. Now,
every differential operator.
Yeah.
Okay, so you're writing it in this form, right?
Yeah.
The x.
Yeah, and why do I write it like this? Because I need to check that this, in fact, obeys the conformal algebra. I have to check it later.
Yeah.
Yeah.
I read the notation like this, which is x u.
Yeah, okay, you're right.
Several times people.
Yes, you're right. The rightist bracket means antisymmetrization with respect to the indices. This is this notation that people use. Yeah.
So, but okay, so you're writing this, the realization in the form of differential
Yes.
operators, right?
Yeah.
However, I can always have an well, assuming that I have a normal mode kind of decomposition, I can always have an equivalent for algebraic form if I take a Fourier transform of any of this, so which becomes an algebraic. Now, when I do that transformation, it becomes algebraic, and I have a matrix representation. So, is it true that every realization?
So you mean the Fourier transform of the momentum? You want to?
Everything here. So the derivative will become a k times blah. So gradient operator will become.
Yeah. Well, then you have RP.
No, it's Fourier transform.
Yeah, but then you have but remember you have the Fourier transform. You are transforming only the P, not the R. RP, you know.
I can transform both.
Yeah, you're right. Yes.
So the realization can be written in terms of representation in Fourier space.
Yeah.
Integral space.
Okay, I guess you could say. Okay, let's look at what Raymond wrote. He wrote it like this. Let's write it like this in the Fourier mode: x mu p nu. You want to write it like this in a pedestrian way. So I guess you can say, okay, I can say that the rows are like x and the columns are like p's.
Are like the modes.
So this is like having a matrix. You call it xp. Is that what you say? Yeah, in a way you could
So
say.
they're the same thing.
Duals of each other. You can say that. Yes, you can say that. Yeah. And of course, you have to have antisymmetry. Yeah. Okay. Yeah. If you want to say it like that. Yeah. Okay. So the momentum operator is represented like this. The dilation. Notice the dilation doesn't have any index, any subindex or superindex. So this is why you contract the mu here with the partial derivative, but the mu upstairs. Or you could have the mu downstairs and raise the mu upstairs here, however you want it, right? Okay, if you don't like it this way, take the x mu here and raise it upwards. And take this mu and lower it downwards, okay? And then this is the boost, look like this. And then, well, this is what I mean by that. So what do I mean that this is a differential realization of the algebra? Well, now, if you want to check that this is true or not, what you do is, then you just take the commutators, you know. Remember? Why do the translations commute? Because if I have, if I have the commutator of two translations, okay, this is, for example, the commutator of two translation operators. In this representation, I represent the operators as differential operators. Then we know that the partial derivatives commute, right? We know that in ordinary calculus, you know, if you're working with non-commutative geometry, they do not commute. But in ordinary commutative geometry, the differential operation commutes. Right? This operation commutes, you know, because if I have a function f, you know, when I take the partial derivatives, you know, the partial derivatives commute. The order of differentiation does not matter, right? So this will give me 0. So this means that this commutator is 0, and this commutator represented the commutator of p nu, okay, and it commutes. Now, if you can do the same thing with the orbital angular momentum. You know, it gets more complicated because with the orbital angular momentum, well, the Lorentz generators minus x mu dd mu. This is one generator. Then you have to have the other generator, which is the x rho. Which letter I use? Sigma, right? I use sigma. Then I have to do the antisymmetrization. Okay, now you want to do the commutator. So this commutator is more complicated because, you know, you have more terms. But when you do the algebra, when you perform the commutation relations, you are going to reproduce the this algebra here. Oh, what did I do? Pardon. You're going to reproduce this algebra. Okay? And why does the metric appear? The metric will appear because you're going to have something like this, a partial derivative of this. For example, remember here I have a covariant index. Here I have a contravariant index. Remember? So in order to be rigorous, I have, and then I'm going to have my metric. Okay. Call it tau. Call it B here. Okay, remember, when I lower indices, I get this, right? But now if the metric is constant, you can pull the metric outside the differential, and you have this metric here. And then you have the derivative of x tau with respect to x mu. And what is that? That is by definition a Kronecker delta, you know? And then you are going to have this. So the metric appears due to the structure of the indices, you know, and this is why you're going to end up with these terms here, 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 and here. Okay?
They're coming from lower
Lower and raising indices. Yes. Yes.
If the space is curved, it's a G mu.
And then you cannot do that, because now you cannot pull out the metric outside the x, because if the metric depends on position, then you cannot differentiate. You cannot pull the metric like that. You will have another term involving the derivative of the metric. So you have to be careful. Remember, this conformal, this algebra acts on your tangent space, really, on your flat space. In curved space-time, we know in curved space-time that the commutator does not commute. Remember, when you work with covariant derivatives, the commutator of two covariant derivatives is not zero. It gives you the curvature. Yes, so then you no longer have the Poincaré group. The Poincaré group only acts on your tangent space, which is at each space-time point. Okay, and this is why you have flat, locally flat, but not globally.
So conformal and concurrent.
Oh yeah, because I'm looking at the translations, rotations. Yeah, remember these are symmetries of your tangent space. Yeah, of course. You know. Remember, the symmetry group in relativity, in gravity, is the group of diffeomorphisms, which is much larger. The group of diffeomorphisms is any arbitrary change of coordinates. And you could have an infinite number of changes of coordinates, so your group is infinite dimensional. The diffeomorphism group is something else. It's much more subtle. Okay, some physical applications of the conformal group. Okay. The largest possible global symmetry of a non-supersymmetric interacting field theory is the direct product of the conformal group with an internal group. Okay, this is only true when you have massless particles. When you have massless particles, you see the conformal group, you see when you have mass, the mass, the inverse of a mass, is like a length scale, when you have the Compton wavelength associated with a massive particle, it's not zero, it's like inverting the mass. So a mass will set up a scale, and if you fix a scale, you destroy your conformal invariance. Conformal invariance really, it doesn't have a fixed scale, it's valid for all scales. So massless, like the photon, doesn't give you any scale, because the inverse of mass equals 0 is infinity. So what happens when you have so in reality you should say when you have really a massless theory like electromagnetism involves a photon and the photon is massless. Even though Feynman thought they had mass. No, the photon electromagnetism, you look at Maxwell's equations, when you write them down, they are invariant under conformal transformations. In 4 dimensions, careful. In 4 dimensions, Maxwell's equation, okay. Now, another application of the conformal group is in critical phenomena. When you look at phase transitions, you see when you reach a critical point, the fluctuation, the size of the fluctuations are going to be arbitrarily large, arbitrarily small. So when you're at the critical point, you're going to have conformal invariance at the critical point. But only at the critical point, because you have fluctuations of any size. There's no fixed size. The correlation length, is infinite. Okay, so people who work in condensed matter, in critical phenomena, they observe conformal invariance at the critical point. And I sent you that paper about turbulence by Polyakov. He claims that conformal field theory is very important to tackle the problems of the onset of turbulence, when the Reynolds number is supposed to be very big? I forgot. Anyway, very big, yeah. Okay, here. Okay, look, conformal invariance is also discovered in 2-dimensional turbulence at a high Reynolds number. So people who work with fluid mechanics.
Actually, the group that I work with, they work with conformal in critical phenomena. So they were studying conformal invariance. What they call SLE. Schramm-Louisville? No, not Schramm-Louisville.
Loebner.
Yeah, Schramm-Louisville equations. Yes.
Okay, now many theories in high energy physics admits conformal symmetry. For example, when you have Yang-Mills theory and when you want to combine supersymmetry, n equals 4 means that you have 4 supersymmetric charges. That's what n equals 4 means. Okay? Ordinary supersymmetry has 1 supersymmetry. Now, let me give you an example of supersymmetry. The typical example of supersymmetry is the Dirac electron. The Dirac equation is nothing but the square root of the Klein-Gordon equation. So that square root procedure in reality is supersymmetric because you are unifying a spin 0 particle with a spin 1/2 particle. So the Klein-Gordon equation, let's say for a scalar Meson spin 0 particle, when you take the square root, you get the Dirac operator. So this is what you call supersymmetry in the old-fashioned way. Now, you could have more than 1 supersymmetric charge, which is called n equals 4. Anyway, don't worry about that. Supersymmetry can be extended to 1 charge, 1 supersymmetric charge, 2, 3, 4, whatever. And it happens that Yang-Mills theory, when you have 4 supersymmetries, it gives you a finite quantum field theory. When you look at the Feynman diagrams and you look at the perturbative expansion of your Feynman diagrams, it happens that the fermionic loop's contribution cancel the bosonic loop contribution, and there's an exact cancellation. So n equals 4 supersymmetry is a finite theory as a quantum field theory. And conformal invariant is very important in that theory. Okay. Then in string theory, remember when you have a string, a one-dimensional object, as it moves through space-time, it sweeps a surface. So this is what you call the world sheet, because a one-dimensional string, as it moves, it sweeps a surface. And okay, this conformal symmetry is also very important in 2-dimensional conformal field theory, And then the real groups, okay, remember yesterday I jumped a little bit. I was just as a reminder that the dimension of the special orthogonal group was n times n minus 1 divided by 2 because the number of antisymmetric combinations. The number of bivectors is this one. The symplectic group, again, the dimension of the symplectic group is given by this number. The unitary group has this dimension. The special unitary group or the special linear group had this dimension. The reason you subtract 1 here is because you have the determinant of those matrices is equal to 1. and you subtract that condition that the determinant is equal to 1. This is why the number of generators is the same as this group, but you subtract 1 because you have to impose a constraint that the determinant of your matrix is equal to 1. This is why you subtract 1.
It's just one degree of freedom.
Yeah, well, exactly.
Set to C,
The special linear group, you know, yeah.
because there is C, so it multiplies by.
No, okay, this is when real groups. Now, when you have complex group, it's more subtle. Yeah. In your book, let me see some here, and if I remember, complex group, okay. Complex group, and then you have quaternionic groups. Now, if you look in your page 50, page 51, you forgot to bring your book? Yeah. Okay, if you look at page 50, page 51, page 52, it gives you the dimensions of your real group, complex group, quaternionic groups. Okay, I will look at page 48, 49, 50, 51, and 52. Make a note to yourselves. Look at pages.
Yes, this is.
Look at pages. Okay, look at pages. Mon Dieu. No, essentially 47, 47, all the way to page 52. Pages 47 all the way to 52. Make a note for yourselves.
Yes.
Okay, there they give you, you know, the list of groups, real groups, complex group, and quaternionic groups. Okay, and he gives you the dimensions of each group, and he explains to you why the dimensions is so and so. Okay, so make sure you make a note for yourself, and it's, you know, it's only a few pages, and it's definitely worthwhile going through it. Of course, when you have complexification, then you have to double the degrees of freedom, that's all. With quaternions, it's more subtle. You have to multiply the degrees of freedom by 4, but remember, when you take the determinant, remember, when you have a quaternionic matrix, the notion of determinant is not really well defined because they don't commute. You have to be careful, you know. Now, here I talk about the general linear group in general, and I give you a matrix representation of the generators of your general linear group. So the standard representation that people use is that each generator of your group is an n by n matrix whose entries are all 0 except at the ith row and the j column where the entry is equal to 1. So imagine you have a matrix. Ij are the generators. Remember, Ij are the generators, and each generators, they are matrices. And because it is a matrix, you have to tell me what the rows and columns are of your matrix. So you choose a matrix whose entries are all 0 except at the ith row and the j column where the entry is 1. So the algebra looks like this, the commutators. The complex special linear group is the complexification of the special linear real group. And remember, this is very interesting. When you complexify the special linear real group, and when you complexify the special unitary group, when you remember, you end up with the special linear complex group. And remember, I said yesterday that sometimes people get confused because they think of the special unitary group as complex because it has complex matrices, and people get a little bit confused. How am I going to complexify a complex matrix, you know? Think about that the structure constants of this Lie algebra are real constants, and the structure constants are real. I have a complex Lie algebra. So in your book, actually, when you look at those pages, it explains well the difference between a real group and a complex group and a quaternion group. Now let me give you some examples. You know, I think, and then we could finish this. Okay, so 2 more slides, huh? Okay, let's look at groups that have 6 generators. By dimension 6, I mean that the group is 6-dimensional. I mean that the algebra has 6 generators. Okay? A typical example, let's look at the Lorentz group in 4 dimensions. The Lorentz group is isomorphic to the complex special linear group. Remember I was talked about the Mobius group because you have 6 generators. The SO4, remember this is the Euclidean rotations in 4 dimensions. Let's suppose that you're working with 4 Euclidean dimensions. Here I'm working with 3 spatial dimensions and 1 temporal dimensions, like Minkowski space-time. Here I'm working with the Euclidean 4 dimensions. So the rotation group in 4 dimensions can be broken up as 2 copies of SU2s. Okay, this is actually, to be rigorous, you see, I copied this from the Gilman, but to be rigorous, I should not use this symbol here because this symbol for many mathematicians is the tensor product.
So that's a direct sum?
This is a direct product, okay? In reality, to be rigorous, this should be a direct product. Don't, you see, because some people confuse direct product with tensor product. You have to be very careful. Remember, to be rigorous, what happens in the book, anyway, is you have to be careful. This is the direct product of 2 SU2s. Don't confuse the tensor product, okay? Don't confuse this symbol with this symbol. You have to be very careful.
The plus inside the circle
The same thing.
That's what you mean, right?
Yeah, direct sum. Yeah, that's what I mean. Yeah. Now,
The plus with a round is like the cross without round.
yeah, it's just crazy. The notation is so inconsistent. What I mean is the direct product. Why? Because this guy, SU2, has 3 generators. SU2 has 3 generators, so 3 plus 3 is 6. Okay? Because 3 plus 3 is not the same thing as 3 times 3. So you see, when you're working with tensor products, you actually multiply things anyway. Now, dimension 10. Dimension 10, for example, imagine you had 2 temporal directions and you have 3 spatial directions. So this group has 10 generators. It's like the simplicity group 4. The SO5 also has 10 generators. Remember, when you look at those pages, 47 through 52, they give you the dimension of each group, okay? So this group has 4 generators because you have 5 times 4 is 20. You divide by 2, you get 10. Dimension 15, for example, a conformal group has 15 generators. This group, imagine you have 3 temporal directions with 3 spatial directions. This is a non-compact group, so you have 15 generators. SO5, 1, imagine you are working with the Lorentz group in 6 dimensions. So you have 5 spatial directions and 1 temporal. And this is also isomorphic to the quaternionic group. Now remember, the G2 is the first exceptional group, which is the automorphism group of the octonions. It has 14 generators. The F4 is another exceptional group, has 52 generators. The E6 is another exceptional group, has 78. The E7 is another exceptional group. It has 133 generators. Your E8, it has 248 generators. Now, don't confuse the generators with the roots. Remember, out of these 248 generators, you have 8 elements of the Cartan subalgebra. And the remaining 240 generators is what make up the 240 roots. So 240...
Simple roots and 240 roots.
I'm sorry?
8 simple roots and 240 roots.
To be rigorous, 8 elements of your Cartan algebra, and 240 roots, Remember, the word simple, you have 8 simple roots, and you have 8 positive roots, 8 positive simple roots, 8 negative simple roots, and the remaining,
The simple roots are not the element of the Cartan algebra.
No.
There is the same number, but...
When we will we'll get into that in full details. What do you mean by simple roots? What do you mean by simple positive roots? What do you mean by simple negative roots? What do you mean by the Cartan-Sab algebra? We'll talk about all that. Now there's another group, which is, remember, it's not simple, which is called the E7 1/2. Have you ever heard of this group? No? 7 1/2? Okay, it's not a simple group. This group was found by Landsberg and another mathematician at Texas A&M University. I think it was Landsberg. Anyway, but remember, it's not a simple group. It can be split up into 3 pieces. You have E7, which is 133 generators. 56, which is the 56 dimensional irreducible representative of E7, and the abelian part. When you add 133 plus 56 plus 1, you get 190. Anyway, I wrote this down out of a curiosity.
It's not 2 SO8?
No, it's not simple. It's just, I wrote this down.
56?
Yeah, it's
2 SO8?
yes.
Where did the word exceptional come from? An exceptional.
The exceptional, these groups were discovered thanks to the octonions. They don't belong to the classical classification of Lie algebras. They're exceptional because they were discovered thanks to octonions. Remember, G2, when you look at the algebra of octonions, the algebra has what you call an automorphisms. In other words, you can switch the generators, interchange them, and you have this, you call this is how this algebra was discovered. Have you heard of the piano plane?
I have heard of piano.
Yeah.
The
Fano plane, yes. There is the 2-dimensional projective group, but in 2-dimension, Fano, F-A-N. I'm sorry, I'll be done soon. Yeah. Anyway, so this is how it was discovered, and then all of these algebras were discovered thanks to the octonions.
And also G2 is a group of the zero divider of the Sedenion.
The Sedenions is not a division algebra,
Yes.
but you are right. The Sedenions has 16 elements, and you're right. The G2 also appear. Yeah, the Sedenions is also very mystical. It's a very mystical group, but it's not it's not a division algebra. It has 0 divisors. How do you call it?
I tried to connect it to the M theory, to the 11 dimensions. Well, remember that the E8 is very interesting because E8 really has to deals with 16 dimensions, really. Yeah, I will get into it, yeah. Because you see, E8 has 120 elements of E8 look like SO16 rotations, okay? Because SO16 has 120 elements. So imagine you have rotations in 16 dimensions, so you end up with 120 elements. And then the 128 has to do with the chiral spinor representation of SO16. SO16 has spinor representations. So you're going to have left-handed and right-handed spinors, so you're going to have 128 of them. So out of 128 and 120, you make up 248. Okay? So I'll be talking in one of the lectures here. I will be talking about that. Okay, so I guess we could leave it out for today, huh? Yeah. You know? Cool. Yeah. So how did it go? It was better than yesterday? Better?
Oh, with standing in front of the camera?
Yeah.
Yeah.
Okay. Hopefully tomorrow it'll be better. Yeah.